So we have here a hollow, right, circular cylinder with diameter 200 millimeters is open at both ends, and that it rests on a horizontal plane as shown. So inside the cylinder are 200 Newton sphere with a radius of, with a diameter of 90 millimeters. So that's sphere A, and for 500 Newton, which is sphere B, it has 150 millimeters in diameter. Neglecting friction, we are going to determine the minimum weight of the cylinder so that it will not tip over. So this one here is the cylinder. So sectional view lang na siya na atong nakita. So it's actually like this one. So something like that. So nadiri ang first cylinder, then the second, the sphere, something na nang a view. So what would be the minimum weight? Meaning the cylinder has weight. So since this is open here, diha ra ang naay surface, of course wala ni siya. But that's the sectional view. So ito lang broken line, something like that. So what would be the weight? So by the way, we're gonna place here the weight because it's always at the center. So if you try to look at the top view of the cylinder, nadiri ang weight. So mo ni ang perimeter sa cylinder, and then mo ni ang weight concentration sa iyang weight, of course. So what we're going to do here is we're going to draw the figure for the cylinder. So this is the surface where the cylinder is acting, this one. So this is the surface, and then we have the cylinder that rests on top. So say this is the cylinder's line. Let's make it a little bit thicker. And let's copy that. Okay. So the cylinder has a point of contact. So the point of contact is from the sphere and the cylinder. So this is point of contact A and point of contact B. So let's say this is from the horizontal, let's call this height B, and here from the horizontal, this is height A. So this is height A, and this is height B. So again, this is the point of contact here and point of contact here. So because the action of the force, so the cylinder, the sphere A will act at this point here. So I'll just call that as RA, and this one also for the sphere B, RB. So what would be, so I'll just move it here. Let's just move. Okay, let's move this one here. So since we have agreed that the weight of the cylinder, so say the weight of the cylinder would always be uniform because it's uniform all throughout its container. So uniform na siya. I'll just represent the uniform to be something like that. So the weight of the cylinder is acted at the center. And by the way, the radius or the diameter of the cylinder, so it's 200 millimeters in diameter. So I'll just write the dimension. So this is 200 millimeters. So the question is, what would be the weight of this cylinder? What would be the weight of the cylinder in order to not tip over the cylinder? So somehow, if we try to consider RA and RB, since RB is quite elevated higher than RA, so it's higher than RA, then RB creates more work than RA. Work means force times distance. So this RB is the element that will cause tipping over. So since the action of RB is towards here, so this one, so since that's the action of RB, the tendency is the body will rotate something like that. It's going to tip over, something like that. So in order to not tip over, we need to get this W. So pasabot, we will be taking moments or moment at this point of the cylinder. So I'll just call this as point C. So we're going to create the equation that it's summation of moment about point C, and it's going to be equal to 0, clockwise positive, counterclockwise negative. So creating moment at C, we have RB clockwise times HB, and then minus RA counterclockwise times HA, and then this one is counterclockwise W, and that's to be multiplied by 1/2 of the 200, which is 100 mm, equal to 0. So in other words, WDI is equal to the force RB. By the way, I'm transposing W to the other side. Force RB times HB minus force RA times HA over 100. This is our working equation. So how do we solve for RA, RB, and HB? So we're going to determine the distances. So we're gonna have another free body diagram of the sphere. So the two spheres. So one is in the lower portion, so this one, and then let's just copy this, and this one is quite larger. Okay, and of course remember that this is the horizontal plane that the smaller cylinder rests. So I'll just make it something like that, and we have forces here. This is force RB, and this is force RA. So remember that to sup- to adhere to equilibrium, it should be in the opposite direction. So as you can see with RA, so as you can see, RA here is to the right, then RA here is to the left. So they're actually opposite. To confirm with equilibrium, and then this one here is to the right, while this one here is to the left. So it's equilibrium. So I hope you got that pattern. So that's equilibrium. So let's just delete this, and then we're gonna measure these distances. Remember that this is HA, while this one here, this one is HB. Then this force or this sphere has a weight. This is weight, pilay weight aninia, 200 newtons, while the other one is 500. So this is 200 newtons, and this is 500 newtons. Okay, how about here? Do we have a contact force that influences the movement of the cylinder? No, wala, because again our cylinder is open at both ends. So kani siya diri buslot na siya the same way here. So kay buslot man, wala siya influence diri sa cylinder. So there is no point of contact there. So let's just delete that. Okay, so these are the only forces that has point of contact with the cylinder. Okay, so what would be the distance HA? So remembering that this is a circle, so it has radius. So therefore, this distance here is 45. Why it's 45? Because according to the problem that the sphere A has a 90 diameters and the sphere B has 150. Okay, so that is 45. So therefore, HA is 45. How about HB? For HB, we are going to create or connect points. So this is the center of sphere B, and this is the center of sphere A. So if we try to connect a line that passes through A and B's center, and then we are going to also create a line that this one here moves down and this one here moves to the right, that one. So we could create a triangle. So how do we make this triangle, or how do we measure this triangle? So from the illustration, we could create a triangle from this one. So let's just copy the formation, and then this one here, let's extend it. Okay, so as you observe, this is the radius of the first cylinder or sphere, which is 45, and the second one is the radius of the second cylinder, which is 75, or sphere rather. So if that's the case, this whole length here of the triangle measures the addition or the sum of the two lengths. That's 45 plus 75. Where did I get 75? It's 1/2 of 150, so this is 120. Okay, how about this distance? Let's call this distance A, and let's call this small letter distance B. So what is distance A and what is distance B? Let's investigate. Remember that this edge of the circle or of the sphere, this one here, so let's just change this one, and this one, let's copy that, and this portion edge of the sphere, this is the measurement of the length of the cylinder, right? The length of the cylinder is 200 millimeters. But what is this length equal to? This length is somehow equal to 45, while this length here is equal to 75, because this is the radius 75 and this is the radius 45. So in this case, the distance between the two of them somehow is the distance A. Therefore, A is equal to 200 minus 45 minus 75. So now we have A. So let's solve for A. A is 200 minus 45 minus 75, and that is 80 millimeters. So mingon mo nga sir, actually B is just the difference between this height and this height. So no, dili na siya pwede. So we have to investigate kung difference ba na siya. But since na naman tayo distance A to be 80, then somehow we could get B from the Pythagorean theorem, that it's equal to the square root of 120 square minus 80 square. So now B is already solved. So this is 120 square minus 80 square. So that's 89.443. So it's 89.443 millimeters. Okay, so now we have that distance already. Okay, so if that would be the case, then we'd be able to solve for HB. Since this is HB and this is 89.443, we could subtract it here, or we could add that 1 to solve for HB. So HPDI is equal to the addition of 45 plus 89.443. So that's going to be 45 plus 89.443, 134.443 millimeters. So we now have the values of HA and HB. Okay, so we're going to now solve for the values of RA and RB. So we need this illustration. This is another free body diagram. So let's say free body diagram of sphere B. So let's proceed in getting the free body diagram of sphere B. Okay, since sphere B raman atong need, then do not forget that let's just delete some of them. This one and this one also. Do not forget that there is a contact point here between the A and B sphere, so I'll call this as reaction. I'll call that as reaction prime. Okay, for reaction prime, basically we need a triangle ganina, because we are going to get the r prime. Our objective is to get r prime and rb, so we will have r prime and rb. Okay, so for r prime we need the inclination of the angle, so I'll just copy the triangle that we created ganina. So this is the triangle from here down horizontal. Okay. And there. So I'll just transfer it here. So this is the line of action of r prime, and let's just make it as a broken line. And we wanted to have the angle and the position from the vertical. So from the vertical here, this one, red. So from the vertical, we need this angle theta. So somehow this is also angle theta, but we have these distances, 89.443, we have 80, and we have 120. So how do we solve for theta? So theta is equal to arctangent function of the opposite over adjacent, 89.443. So theta is it 89 point? Yes. So theta is equal to arctangent of 80 over 89.443. So that's 41.81. 41.81 degrees. Since the naman tayo angle, we will get now the component of r prime. So this is r prime cosine of theta, and this one here, this is r prime sine of theta. So using summation of forces vertical and horizontal, we'd get the value of rb prime and r prime and rb. So summation of forces vertical equal to 0. We cannot use summation of moment. So although naa siya distances, but it's quite complicated if you're gonna use the summation of moment. So just consider this as a concurrent force system. So upward positive, downward negative. You have r prime upward cosine of 41.81 minus 500 equal to 0. So r prime is equal to 500 over cosine of 41.81. So r prime is this one, 500 over cosine of 41.81. That's 670.82. 670.82, and this is in newtons. So therefore, we can solve for RB by having summation of forces horizontal equal to 0. So to the right positive, to the left negative. So R prime is to the right, sine of theta minus RB equal to 0. Transposing RB to the other side, we will have RB equal to R prime 670.82 sine of 41.81. So RB is now equal to 670.82 sine of 41.81. The answer is 447.21 newtons. Okay, so that's 447.21. So we now have the value of RB, which is important with the equation here. So we have RB already, HB and HA. So we need now RA. How do we solve for RA? All we have to do is do another free body diagram. So free body diagram of sphere A. So for sphere A, let's just copy this. And this one. So let's just delete some. Kung wala yung mga gamit. Okay, so this is our RA, and of course we have this point of contact here, wherein R prime also is acting, so it's now to downward because we have here upward R prime, so it's upward, and then it's now downward here, it's downward, so this is R prime. And then from the vertical na ang angle of inclination, so this is theta from the vertical. Okay, so get the component of R prime. We have R prime sine, cosine of theta, and R prime sine of theta. So theta is 41.81. So let's now solve summation of forces horizontal, because our objective is to solve for RA. So to the right positive, to the left negative. So you have RA to the right minus R prime sine of 41.81 equal to 0. RA is now, so 670.82 sine of 41.81. So you have RA, so it's 670.82 sine of 41.81. It's 447.21. Okay, so yeah, that would be 447.21. Oh no, yeah, 21. So this is in newtons. So now we have RA. How do we know that our RA and RB are correct? Actually, they are correct, because if we are just going to consider this equilibrium, so, or this free body diagram, if we try to have summation of forces horizontal here, there are two forces horizontal, so therefore this is RB to the right minus RA to the left equal to 0. Therefore RB is just equal to RA. So it satisfies the equilibrium. That's why we obtained the same answer, 447.21 for both RA and RB. So this time we're now going to use this equation so we can solve for the weight. What would be the weight or value of the weight in order not to tip over the cylinder? Okay, let us substitute. So W is equal to 447.21 times HB, it's 134.443. So 134.443 minus 447.21 times 45 HA divided by 100. So now we have the W, and the W is equal to 447.21 times 134.443 minus 447.21 times 45 divided by 100. So it's 399.998, or somehow this is 400 newtons. So W is 400 newtons. This is the minimum weight that the W should have, or the weight of the cylinder should have, in order not to tip over the cylinder. So this is example.